In 2021, a single Chinese crane lifted 4,500 tons, shattering every previous engineering record and pushing human precision to 0.5 millimeter. By 2024, giants even larger could drive themselves 500 kilometers across open highways, cutting project times and costs overnight. Billions now hinge on these machines. One calculation off means disaster, and yet their mobility could rewrite the economics of global energy. How did China leap so far ahead? And where does this race for power lead when steel and physics finally reach their limit? Steel towers arch skyward, dwarfing city blocks and shipyards alike. At the heart of this engineering contest stands the Sany SCC45000A, a mobile crawler crane whose statistics read like science fiction. On October 13, 2021, it hoisted 4,500 tons in a single lift, an act that required 98,000 ton-meters of force and a boom stretching up to 216 meters. The foundation of this feat is a counterweight system totaling 2,200 tons, balanced with laser alignment to within 0.5 millimeter. Operators describe the process as walking a tightrope with steel and concrete, where a deviation smaller than a fingernail could send $500 million in equipment crashing to the ground. Behind the numbers, the SCC45000A is more than just brute force. Its modular design means 95% of its parts are interchangeable with Sany's other ultra-heavy cranes, allowing it to be split into two 2,000-ton machines for complex sites. The logistics are staggering. Moving the crane demands at least 200 flatbed trucks, and assembly is a ballet of engineers, riggers, and sensor teams. According to Sany's lift planner, every major operation is a rehearsal for disaster. Redundant systems, backup crews, triple checks on load sensors, and redundant rehearsals are mandatory. One missed reading, and you lose everything. The XCMG XGC88000, close behind in the global rankings, boasts a 4,000-ton capacity, powered by 3 Cummins engines, delivering nearly 2,000 kilowatts. Its boom also stretches 216 meters, and the entire structure is designed for rapid reconfiguration on petrochemical sites and offshore platforms. In these environments, the load moment, the product of weight and distance from the pivot, becomes the ultimate test. A 98,000 ton-meters moment means the crane must counteract forces that would buckle most city bridges. The margin for error is measured in tenths of a millimeter, monitored by laser-guided systems and ground settlement sensors that halt operations if the Earth shifts by as little as 2 millimeters. On the nuclear frontier, the Sany SCC36000TM specializes in precision. This 3,600-ton giant is engineered for reactor dome placement, where 5-centimeter accuracy is not a luxury, but a regulatory mandate. Its laser guidance system, combined with adaptive control algorithms, synchronizes every movement of the boom and counterweight. During a typical reactor lift, ground teams monitor live data from gyroscopes and strain gauges, making split-second adjustments to keep the load perfectly vertical. The consequences of error are measured not just in dollars, but in lives and national safety. Together, these 3 cranes represent over $15 billion in market value and the physical limits of what current materials and engineering can achieve. Each year, they complete dozens of major lifts, with documented safety records built on thousands of hours of incident-free operation. Yet the industry has reached a point where adding more steel or height is no longer the answer. The race for raw tonnage has collided with the boundaries of physics. What comes next is not just about size, but about how these giants move, adapt, and redefine the economics of construction and energy on a global scale. On a cold December morning in Inner Mongolia, a machine the length of a blue whale rolled off the expressway under its own power. The Sany SAC40000T delivered just weeks earlier, arrived at a wind farm site not by train, nor by a convoy of hundreds of trucks, but as a single, road-legal unit. This was no ordinary move. With 9 axles and 540 wheels, the SAC40000T is permitted on Chinese highways at speeds up to 75 kilometers per hour, a feat that would be impossible for any Western rival. The project manager overseeing the pilot described the scene. "Instead of waiting weeks for assembly, we started lifting turbines within 2 days. The savings were immediate." In the past, relocating a crane of this size between wind farms meant shutting down roads, dispatching 200 or more trucks, and spending over a month on disassembly and reassembly. Each move could cost $2 million in labor, permits, and lost time. With the SAC40000T, the team covered 500 kilometers between sites, cutting deployment from 45 days to just 12. During the 6-week pilot, crews installed 18 turbines, each tower rising over 150 meters without pausing for the traditional bottlenecks of logistics. The difference was measured not just in time, but in money. The reduced downtime meant the wind project generated power weeks ahead of schedule, unlocking revenue that would have otherwise been lost. Logistics contractors on site noted the ripple effect. Fewer trucks meant less congestion, lighter road wear, and no need for police convoys or route closures. The crane's design, distributing weight across 540 wheels, allowed it to cross bridges and highways engineered for China's new energy corridors. Insurance underwriters, usually wary of moving such massive loads, reported lower claims for in-transit losses compared to traditional crawler cranes. The SAC40000T's mobility is more than an engineering showcase. It is a calculated answer to the demands of China's fast-growing wind sector, where a missed weather window can stall a project for months. For project managers, the ability to relocate a 4,000-ton crane in days, not weeks, means capital is freed up and assets are never idle. Yet this mobility comes with boundaries. The same 9-axle, road-legal design that powers across China would be blocked at the border in Europe or the United States, where axle weight limits and fragmented permitting regimes make such machines illegal on public roads. For now, the true impact of the SAC40000T is felt where modern highways and regulatory fast tracks align, primarily in China's interior, where wind farms race to meet national energy targets. As the industry pivots from pure lifting power to deployment speed and cost efficiency, the SAC40000T stands as proof that the future of heavy lifting will be decided as much by how quickly a crane can move as by how much it can lift. In the words of the Inner Mongolia project manager, "We used to plan around the crane. Now, the crane plans around us." Diesel engines have powered the world's largest cranes for decades, but the industry's appetite for fuel is staggering. A single heavy lift shift can burn through 2,400 liters, equal to the daily emissions of 80 passenger cars. With 2030 carbon neutrality targets looming in both China and Europe, regulators are forcing manufacturers to rethink every aspect of crane propulsion. In March 2025, XCMG introduced the XCA60EV, a 60-ton hybrid crane designed to cut fuel consumption by 65%. It is a partial solution, effective for smaller lifts, but the physics of batteries and motors have yet to scale for the true giants. For cranes above 1,000 tons, diesel still dominates, as the energy density required for multi-hour operations remains beyond current battery technology. The push for electrification is most visible in Europe, where Sarens announced the SGC170 in July 2025. This 3,200-ton ring crane, slated for the Hinkley Point C nuclear site in the UK, runs on 12 grid-connected electric motors, delivering zero on-site emissions. but the trade-off is clear. After 4 hours of lifting, the crane requires 8 hours to recharge. The grid dependency poses a risk. Any power outage can halt critical lifts for an entire shift. As one Saren's project lead put it, you can't afford to gamble on the grid when a billion-dollar reactor dome is hanging mid-air. Hydrogen fuel cells are being tested as a possible answer. XCMG's prototype, reported in early 2025, promises 12 hours of continuous operation on a single fill, but the technology is still in pilot phases. For now, electrification is driven by regulation, not by market demand. Every incremental gain in efficiency has become a prized advantage in export bids, but no one claims the race is over. The world's largest cranes still run on compromise, balancing power, emissions, and operational risk, one lift at a time. In 2006, China's State Council added super heavy cranes to its national priority technology list. That single policy decision unlocked a wave of state-directed support. Provincial governments offered free land and tax breaks to any manufacturer willing to take on the challenge. State banks, acting on central directives, extended loans at just 0.5% interest, rates that Western rivals could only dream of. By 2010, the consequences were already visible. Nuclear and petrochemical projects across China stalled for months, waiting for foreign cranes that never arrived on time. The strategic bottleneck was clear to policymakers and entrepreneurs alike. Liang Wengen, a former arms factory manager from Hunan, recognized the opportunity. With deep ties to both the military-industrial complex and provincial officials, he secured favorable terms for his company, Sany. His approach went beyond cheap capital. By vertical integration of supply chains, steel, sensors, control software, Sany could outpace Western competitors who relied on quarterly returns and fragmented suppliers. The result? By 2015, Chinese-built cranes surpassed 3,000 tons in rated capacity, a milestone that broke the last technical barrier held by the West. A policy analyst reviewing this period describes it as the Great Compression. 2 decades of Western development replicated in less than 10 years through a combination of state capital, patient investment, and relentless iteration. By 2025, the numbers told the story. Chinese manufacturers controlled 61% of the global super heavy crane market, a dominance built not just on engineering, but on the machinery of policy and finance. Liang Wengen's net worth soared past $17 billion, a testament to how state priorities can reshape entire industries. The economic engine behind China's crane empire was never just about steel and hydraulics. It was about aligning national ambition with financial muscle. 12 new heavy crane models rolled out of Chinese factories in 2024, each one a response to relentless competition among Sany, XCMG, and Zoomlion. An industry analyst described the pace as a product cycle on fast forward, with rival teams racing to outdo each other in capabilities and cost. XCMG has carved out a lead in petrochemical plants, fielding self-assembling cranes that minimize risk around flammable modules. Sany leads nuclear construction, leveraging laser guidance systems capable of 5-centimeter placement accuracy, a standard verified on reactor sites by independent inspectors. Zoomlion, the third force, is pushing vertical reach boundaries, setting an 82-meter aerial record for offshore wind platforms. This rivalry is not just about technical bragging rights. Export records show that Chinese cranes now enter global bids at prices up to 40% below Western equivalents. Procurement directors in Southeast Asia and Africa confirm that choosing Chinese means both lower cost and more frequent technical upgrades. According to one analyst, internal competition compresses years of Western development into a matter of months. Yet as the machines grow more complex, safety architecture has become just as fierce a battleground as raw power. A senior safety engineer explains that every lift is monitored by triple redundant load sensors. If even one disagrees, the system locks out movement instantly. 5 wind sensors spaced along the boom halt operations if gusts exceed 12 meters per second. Laser ground settlement monitors detect shifts as small as 2 millimeters, preventing catastrophic tipping. AI cameras watch exclusion zones, sounding alarms if a worker enters danger. Gyroscopes and strain gauges feed adaptive controls, updating 100 times per second. These layers of redundancy are refined through 50 or more major lifts per crane each year, shaping a safety record that underpins every export contract. In the words of the safety engineer, trust is built not on claims, but on thousands of incident-free lifts, logged and reviewed after every job. A floating platform rises and falls with the gray-green swells of the East China Sea. On deck, the XCMG XGC88000 stands ready, its boom reaching out over water deeper than most city towers are tall. In August 2025, project planners in Jiangsu prepared for a lift that would test the limits of both steel and sea. The target was a 26-megawatt offshore wind turbine with a 185-meter hub height and a nacelle weighing nearly 1,000 tons. Above, a rotor sweep of 77,000 square meters would soon claim the title of the world's largest. This scale demands more than raw power. Each of the 200 bolts securing the nacelle had to align within millimeters, all while wind gusts pushed at 15 meters per second and the deck pitched beneath the crane's hydraulic wave-dampening legs. The planner in charge described the challenge, saying that every lift is a negotiation with the weather. "We have a 2-hour window, miss it, and you lose a week." Marine adaptation is now standard for these giants. Corrosion-resistant alloys shield every joint, and hydraulic legs anchor the crane against unpredictable swells. As global offshore wind capacity heads for 380 gigawatts by 2030, every successful installation translates to new power for millions. The real contest is not just about who builds the biggest turbine, but who controls the machines that make such projects possible. In this race, mastery of heavy lift technology is shaping the future of green energy one lift at a time. Chinese crawler cranes now work on construction sites from Lagos to Lahore, but the real power lies in the agreements that travel with them. As of 2025, 847 super-heavy Chinese cranes operate across 67 countries, their presence secured by $66.2 billion in belt and road contracts signed in just the first half of the year. These deals go far beyond hardware. Procurement contracts routinely require a 20-year service and maintenance commitment, embedding Chinese technicians at project sites for decades. At Pakistan's Chashma nuclear complex, the reactor dome could not be placed without Sany cranes, and the contract stipulates that only certified Chinese parts and staff can be used for critical operations. If a host country tries to switch suppliers or use non-Chinese components, warranties and operational certifications are immediately voided. A procurement official involved in a recent African refinery project put it plainly: "We get the crane, the financing, and the staff. But after that, we depend on China for every major lift, every part, every inspection for the next 20 years. These service clauses ensure that each crane is more than a machine. It is a long-term lever of influence, locking in technical standards and shaping infrastructure decisions for a generation. The result is a dependency that cannot be unwound with a single contract or a change in government policy. Every major lift becomes a renewal of that relationship, cemented by technicians, spare parts, and the quiet presence of Chinese engineers on site. Inside a boardroom in Rotterdam, a Western crane executive studies market charts that tell a harsh story. In 2005, European and American manufacturers held 78% of the global heavy lift crane market. By 2025, that share has plunged to 38%. The industry's most powerful Western-built crane, Big Carl, a 5,000-ton stationary ring crane, stands at Hinkley Point C in the UK, but its fate is sealed. Assembled once, it will be dismantled and scrapped after the project. Mobility, once the Western edge, is now China's domain. Faced with this reality, Western firms are pivoting to specialized niches and digital innovation. Liebherr caps its largest mobile models at 3,000 tons and focuses on premium European contracts. Manitowoc and Tadano have retreated to lighter segments and service agreements. Their strategy now revolves around software, AI-assisted lift planning that calculates rigging and load paths in seconds, and digital twins that predict maintenance needs before a fault brings a project to a halt. An academic specializing in construction robotics points to remote operation trials, cranes piloted from hundreds of kilometers away, reducing labor costs and safety risks. But the stakes run deeper than the next contract. Security memos from U.S. port authorities warn of potential surveillance risks from Chinese-manufactured cranes embedded in critical infrastructure. The debate intensifies as projections show Chinese manufacturers could reach 75% of the global super-heavy crane market by 2030. The policy choice is stark. Invest billions to rebuild domestic capacity and regain control, or accept long-term dependency on foreign machines for the infrastructure of the future. Right now, over 60% of the world's super-heavy lifting power answers to one nation, reshaping global infrastructure, supply chains, and energy ambitions. As the next decade pivots on clean energy and rapid construction, whoever controls these machines controls the future's foundation. The question is not just about engineering muscle. It is about who sets the rules for the world we are building next.